Welcome back. We are discussing how to get the eigenvalue and eigenvectors of a square matrix, which will be useful for exploring available quantum states if the Hamiltonian is known, as long as we can convert the Hamiltonian in the matrix representation. And we have seen that there is a characteristic equation which one can use to get the eigenvalue and eigenvector of a square matrix. But that using a characteristic equation, it becomes little difficult when we have large matrix, and usually all the under grid representation, the matrices can be of the order of, let us say, Hamiltonian matrix would be of the order of 3000 by 3000, which is a very large matrix. This here we are using only 2 by 2. So for such a large matrix, it is not possible to do use this characteristic equation method. What we need to do is that we have to use this diagonalization method. And what does it mean by diagonalization? What is the basic idea behind it? What is the origin of this idea? We will discuss right now. We have already seen that for this matrix we have two normalized eigenvectors. And if we have these two normalized eigenvectors, what we will do, I will now define a matrix like this. U equals, I will take this in one column, 1 by square root of 2 minus 1 by square root of 2. I will take this column, sorry, in the column. Another matrix, another eigenvector we have is 1 by 2 square root of 1 by square root of 2. So, I am defining a matrix now, new matrix. Why I am defining this new matrix, I'll reveal very soon. Let us say I have this matrix where the first column I have taken from this normalized eigenvector, and the second column I have represented by this eigenvector. I have just defined a new matrix, and after the definition I will try to find out U inverse of the matrix, of that matrix. So, I am now defined 2 by 2 matrix I have defined, and I would like to find out inverse of that matrix. And inverse of the matrix can be found only by this equation. U inverse is going to be always a unit matrix. So, 0 0 1, diagonal element should be 1. So, how can I get that? I have to just multiply. So, which means that let us say I have this matrix 1 by square root of 2, then 1 by square root of 2, then minus 1 by square root of 2, then 1 by square root of 2, and then inverse I say A, B, C, D. I do not know what is the value of each element. This is going to be new matrix, but I know the final form is going to be 0 1. This is the form. So, I have again matrix multiplication, and if we have the matrix multiplication, this multiplication can be done by A by root 2 plus this is C by root 2, then B by root 2 plus D by root 2, then there will be another element, there will be another element. You can go ahead with this multiplication, and this is going to be now 1 0 0 1. And if we simplify, I have jumped the step, I am not showing these elements. You can do it as an home assignment, and if I do that, and then finally what we need to do is that we have to equate elements. This element should be equal to this element should be equal to this element. We have to equate elements of left hand side and right hand sides. If we do that, then finally we will be able to get U inverse A, we will be able to get A equals in fact few equations we will get first, such as a plus c equals square root of 2, then b plus d equals 0, then minus a plus c equals 0, and then minus b equals d equals square root, and we can solve this finally, and if we solve it we will get this u inverse. So, finally what we get is u inverse would be of this form. I have shown the procedure already. So, I will write down the final form of the u inverse which we will get. The final form of the u inverse would be one by square root of 2 minus 1 by square root of 2, 1 by square root of 2, and then minus plus 1 by square root of 2. So, this is going to be the u inverse. And what we see is that if we compare now this matrix and this matrix, if we compare, we see that u dagger, if I try to find out u dagger, which means the adjoint of the u matrix. This is the u matrix I have defined. Adjoint would be the exchange of row column and then take the complex conjugate. Here all elements are real. So, we do not need to worry about complex conjugate, but we can change the position. So, this is going to be minus 1 by square root of 2, then 1 by square root of 2, then 1 by square root of 2. This is going to be the u dagger. What we see here from this exercise is that u dagger is actually u inverse, and whenever you have u dagger equals u inverse, we have defined that operator, or here operator will be represented in terms of matrix. So, we call it u matrix is an unitary matrix that we have already presented. Is u has to be unitary matrix because they are equal. So, the matrix which I have defined with the help of this eigenvector, individual eigenvectors, that matrix is turned out to be an unitary matrix. That is going to be an unitary matrix always. So, the matrix which I am forming with the help of the normalized eigenvector and normalized eigenvectors of a matrix will always be an unitary matrix. Now, I will define this AU. I will multiply this AU. So, this is equal. Now, I will find out AU. What is AU? AU is going to be, A matrix is 2 1 1 2, and U matrix is going to be 1 by square root of 2, 1 by square root of 2 minus 1 by square root of 2, 1 by square root of 2. This is the matrix I have, and if I do that, if I multiply it, I am not showing it explicitly, I will just write down the final form. You can do it on your own once you know this matrix multiplication. 3 by square root of 2. So, this is going to be AU, and now I will multiply U inverse AU, which means I have now U inverse is nothing but 1 by square root of 2 minus 1 by square root of 2, 1 by square root of 2, 1 by square root of 2. This will be multiplied by 1 by square root of 3 by square root of 2 minus 1 by square root of 2 and 3 by square root of 2. If I multiply that, then what I get is 0, 3. That is quite interesting. What I get is that lambda 1, 0, 0, lambda 2. I get a diagonalized matrix, a diagonalized matrix, diagonal matrix has aii value, finite values I have, but aij, all aij's is going to be 0. So, all off diagonal elements would be 0, only diagonal element will exist, And those diagonal elements what we are seeing here, if I perform this operation U inverse A U, then I actually get back the eigen values. So what we are learning from here is that if I have a matrix like A, which can be a Hamiltonian matrix, but if I have a matrix A, I have to look for this unitary matrix U. If I can look for it, how can I look for it? I can look for it such a way that this U inverse A U, this operation, this linear transformation will finally give me the eigenvalues. And how can I get the eigenvectors? Eigenvectors are already given within this U matrix. So all I have to find out is this U matrix, unitary transformation, and that's why it's called unitary transformation. So diagonalizing a matrix is nothing but finding out this unitary matrix associated with this square matrix, because if I find out this unitary matrix, immediately I'll be able to get the eigenvectors and eigenvalues. So this is quite interesting way of interesting approach, and numerical implementation is done with the help of this diagonalizing a matrix. So if I diagonalize a matrix, what I have learned here is that diagonalize a matrix is nothing but find out eigenvalue and eigenvectors. So I can find out the spectrum of the system. And this diagonalization is done with the help of this linear transformation. U inverse A U equals lambda, where U contains the eigenvector information, lambda contains the eigen value information. So what we have pretty much covered the kind of linear algebra we need to explore the quantum system, and we will ask this question. What we have seen is that diagonalizing a matrix is a convenient way, and we have got an useful perspective of diagonalizing a matrix. So if I have a matrix, I have to find out then U, that is going to be unitary matrix, and that U will contain the eigenvector. And if I do that, then this linear transformation will give me associated eigenvalues. This is matrix equation, which means that each one is actually representing a matrix. This is an unitary matrix, this is the matrix which I have, and this is another unitary matrix, and this is the matrix which is incorporating or containing that eigenvalue information. So the role of the unitary matrix U is that it transforms the matrix A into a new diagonal form lambda in which diagonal elements represent the eigenvalues of the matrix A, and the columns of the matrix U represents the eigenvector of the matrix A. So that's the meaning of this unitary transformation. So we'll move forward now. This is pretty much what we need to review for the matrix algebra, because this similar kind of matrix algebra will be used to represent the Hamiltonian operator, and we said that we have to perform this matrix representation of the wave function and the Hamiltonian operator to get the numerical solution. So this is the final goal of this module, to represent this function and Hamiltonian operator in the matrix form. So wave function, we have already shown that wave function can be represented on the grid, and if we represent the wave function, this is a nice example we have shown. If the wave function psi, the psi x can be represented, psi x is a continuous function by nature. That's the postulate of quantum mechanics. But on the grid representation, we will first take the grid of the x-axis. The problem domain is divided. So grid means x is not continuous anymore. Certain values of x is taken with a specific separation. So in the grid representation, this entire x-axis is divided into discrete grids, that is shown here, and on each grid the wave function value will be calculated. So wave function is now represented as a discretized wave function, and the separation is delta x. We have shown in the Python tutorial, one of the Python tutorials, that this, if I have n number of grids, if the x coordinate within this range x minimum to x maximum, within the range, I can use minus infinity to plus infinity. It is not possible numerically. I cannot implement minus infinity to plus infinity. We have to always select a range which is finite. So this is the finite range we have selected. This finite range of x coordinate or x axis, within this range, this is minimum, x maximum. Within this range, this x coordinate is divided by suitable small step size, that is delta x. So that's the way we produce this grid. And once we produce this grid, let's say I have n discrete values of x within this range. So if we have this n discrete values, n can be represented as 1 plus, this we have shown already in one of the Python tutorial, 1 plus x max minus x minimum divided by delta x. This many points will have, and at each point on each grid we will represent this continuous wave function psi x. So I will, what I'll get, I will get at x naught I'll get psi x naught value, at x1 psi x1 value, at x2 I will get psi x2 value, and so on. And we said that within this grid representation, what I can do, these values I can call it as y naught, y1, y2, like this. These values can be represented in a column matrix, y0, y1, y2, like this, yn minus 1 column matrix. And the moment we represent on a discretized, once we have discretized the wave function, so we know the matrix representation of the wave function now under grid representation. Under grid representation, matrix representation of the wave function is a column matrix. So once we have discretized the wave function on the grid, because Hamiltonian operator, this operator is having kinetic energy part plus potential energy part. Kinetic energy part having a derivative operator. So first question, in order to address, in order to convert this Hamiltonian operator, in order to represent the Hamiltonian operator in the matrix form, the first thing we have to understand is that this Hamiltonian operator is going to act on the wave function. So when H is going to act on the wave function, its kinetic energy part is going to act on wave function. And kinetic energy part has this derivative on, so derivative will be acting on the wave function. So question is, if this is, question is, how do I represent this particular derivative operator in the matrix form? Then only we will be able to do this operation. So our next question is, what is the matrix representation what is the matrix representation of this derivative operator which will be acting on this wave function? In the matrix form, we will be able to do the matrix multiplication if we know the matrix representation of the derivative operator. In order to find out the matrix representation of the derivative operator, we will introduce finite difference method. Under the finite difference method, what we will do, we will assume that the function, a particular function can be expressed in terms of a Taylor series expansion, where I know the function value at x naught and also all derivatives I know. So I will have function's derivative at x equals x naught delta x plus, so I am using a Taylor series expansion to expand the function's value. Similarly, d2f second derivative also exists at x naught equals value. So, I have a function and this function value at x naught is known, its derivative, all derivatives are also known, and if it is known, then I will be able to express this function fx naught plus delta x in terms of Taylor series expansion, plus I have this expressions. So, what I will do right now, I will represent this first derivative dx fx at x naught is going to be nothing but f x naught plus delta x minus f x naught divided by delta x minus, I have second derivative, I have factorial 2 here also. So, I have second derivative at x naught multiplied by delta x. Why this is going to be delta x square. So, delta x and plus other terms also there. So, what we will do, as delta x is very small, I can neglect these other terms because that is going to be delta x square, then delta x cube, all these terms can be neglected, and I can say that approximately I can write down this d first derivative of this function at x naught equals f x naught plus delta x minus f x naught divided by delta x plus an error would be proportional to delta x. This is called truncation error. So, this is represented by O delta x is called truncation error, and as long as delta x is small, this error would be also small. So, what we have just represented this equation, this is representing the first derivative under finite difference method. First derivative finite difference method where error is proportional to delta x. This is called the forward difference expression. This is called forward difference . Why this is forward difference expression? Because we need the function value in order to find out this first derivative of the function. I need the function value where we are interested. This is the function value where we are interested to find out the derivative, because derivative is being calculated at x naught. So, function value I need at x naught. In addition to that, I need the function value at a small step forward. This one also I need a small step forward, a small step forward. So, because I would like to find out the derivative at x equals 0, I need the function value at x equals 0, plus I need, in addition to that, I need the function value at a point small step forward. That is why it is called forward difference expression. Similarly, backward difference expression can be obtained, and in that case the expression would be following. Expression would be f x naught minus f x naught minus delta x, and that is also possible to get that. This is called backward difference expression. And similar way we can think about central difference as well, and that can be obtained by following. I will take the forward difference first, equals f x naught plus df dx at x naught delta x plus 1 by d2f dx2 x naught delta x square plus dqf dx cube x naught delta x cube plus. This way I have one forward difference and then I have backward difference as well. Backward difference can be obtained by this f x naught minus df dx at x naught delta x plus second derivative at x naught delta x square plus this is going to be minus third derivative at x naught delta x cube, like this way. So if we take the, if we subtract these two expressions, what we get is that f x naught plus delta x minus f x naught plus minus delta x. We subtract it, I get, so this 2 will be gone and only thing is this 2 will get. So I'll get twice of the first derivative at x naught delta x plus this part will be also gone. So I'll remaining part, this third 2 divided by factorial, then third derivative at x naught delta x cube plus, like this. And because delta x is assumed to be very small, I can neglect other terms also because they are too small. I'll neglect other terms here and I truncate it here. So in the end what I get is that the first derivative can be represented in following way: df dx at x naught equals nothing but f x naught plus delta x minus f x naught minus delta x divided by 2 delta x plus I will call an error which is delta x square. This is cube, but I have to divide by delta x, and that's why I get an expression with delta x square. So what we see is that this is called central difference expression. Central difference expression. Central difference. This is called central difference expression, and in the central difference expression what we see is that this is a better way of finding first derivative because this error is now proportional to delta x square. So, by selecting a very small delta x, I will be able to reduce the error quadratically. Previously, in the forward difference and backward difference, both error were linear. So, it will drop down linearly, but here drop down quadratically, it will drop down drastically. That is why it is better if approximation. So, central difference expression is a better approximation for doing this derivative. And so, after learning, remember we have to go for the second derivative. It is not the first derivative we are interested in, it is the second derivative we are interested in, because kinetic energy operator has second derivative in it. So, we have to get the second derivative. I represented the first derivative to get the idea of finite difference method, and three different expressions we can get. One is called central difference, another one is called forward difference. So, these are the expressions we need to get. I will continue this module in the next session.